How much is
It's like $40. Yeah. Which would be. It costs like your whole budget.
Yeah, that would be your whole budget.
Another expense, I found it. But if it's filament you already have.
If it's filament you already have,
That it was, if you had it printed, it counted.
yeah, but yeah, if printed, it's counted as something you already have, but if you use it, then you should put it in your budget, because it's a very expensive thing. Okay, I have no Milo, I have a Caitlin. I have no Lucas, I have no Xander, that's everybody I have, okay.
something about.
Turn that,
What?
let me check my drying glass in the oven, and we'll be good. On.
Oh, why?
So good.
That's great.
Yeah, no.
You have a Walmart order coming?
Yeah.
Do you want to help me?
Bring it on my phone, I'll be like, this is so funny.
Everything. Starting people.
Hamburger.
Welcome to Q4, you made it, home stretch, we're almost done, yeah? Yes,
No, I graduated.
we're almost done, she's like, no, I'm leaving. I'm moving into another world entire, hey, it's cool though, it's cool that you're graduating, like, it's a good thing. You're gonna be left alone, you get the whole house to yourself.
I know I do. She's like, I'm always at dance or work or campus.
This is true.
I'm always at you or that. No? Well, one day. No.
Well, we're good, so, okay, couple quick things, so the test. I will tell everybody that if you want to turn in extra credit for the test, I'll give you till 5 PM today, but then I'm gonna start cranking out progress reports.
I work
Okay.
until 6.
Yeah,
Until 7. Cause I work for the 6.
maybe, if you text me and remind me.
If I want to do it.
If you want to do, yeah, let me know if I'm waiting on you, okay, so yes,
How much question for extra credit?
you got yours, yours, well, I can get max of 100, nobody gets over 105 percentage wise, so it depends on how you can answer up to 5, right? It depends. I'm being a little generous with this one because this was a challenging test, right? Like, very few of you were like, aced it. Also, I think not quite as many of you as I had hoped truly paid attention to the virtual lesson, because the little trick question on there about the virtual lesson, not a whole lot of you got, what's my instrument?
You don't play when you sing.
My voice is my instrument. We talked about, it was when we were talking about resonance and pitch and all that. And I showed you a gross picture of my vocal cords, like, so those of you who, yeah, if you paid attention, you saw that.
Remember.
Oh, very cool.
Yeah, I thought so. All right, so we're starting, hang on a sec. We're starting into chemistry. This is a light touch on chemistry before we dig in next year. Very light touch. You have the next 2 weeks off, right? Everybody knows this. We have spring break, a 2-week spring break. Enjoy it. No school. Hopefully you get a good break. Do you get a good break all around?
Yeah.
Everything? Cool. Excellent.
I still.
You still have classes.
I still have class.
Did you have a question, Yusuf?
Oh, yeah, so I think human voice is that kind of.
Yeah, you're good. Also, just a reminder to everybody, if it's an open-ended question, right? Like a free answer question, then I can't guess all the possible answers you're gonna give me. So what I do is I put my best guesses in as to what you might say, and if you happen to say exactly what I said, then it will automatically count it right. If you don't say it exactly like I said it, it will automatically count it wrong. Rest assured, I go over the whole test and look at everything you got wrong. And if any free answer questions are wrong, I read them and I make sure that you actually have an appropriate answer. Maybe I didn't guess it, but you actually have an appropriate answer. Like somebody for the solenoid question, I had just put car. Somebody put a car. Of course, it counted it wrong. That doesn't mean you're not going to get your points. You will get your points. I will go back and look. Now, always review your tests because there is a chance that I missed something. And if I missed something, I would hate for you to not get credit for it. There was somebody caught one yesterday that I did miss. Like I had failed to give points where I should have given points. So always look over your test. Always review them. Oh, he's talking to Eunice. Hey, what's up? All right, so let's start in. And then we have an activity at the end of class, which should be fun. Okay, we have a game. So we're going to start with talking about classifying matter. So pure substance, every substance of a given sample has the same properties because a substance has a fixed uniform composition. What's the definition, Emily?
Matter that always has the same composition.
Yeah, matter that always has the same composition. So basically it's a particular compound. Like for example, water is a pure substance. You start adding chloride to it or whatever, or salt to it, then you get something other than just water. An element has a fixed composition because it only contains one type of atom. Who can define element, Bailey?
A substance that cannot be broken down into simpler.
Right, now, notice that it says substance that cannot be broken down into simpler substances. So these are our elements. Ta-da! Very cool. We're gonna be talking a lot about this guy, okay? So these are our elements. Now, take, for example, water. We all know water is H2O, 2 hydrogens, 1 oxygen, right? That's water. You can break water down into simpler substances, which are hydrogen and oxygen. You can break an element down into its particles, but that changes the substance substantially, okay? Once you change, if you start messing with oxygen and you start breaking it down, it's no longer its elemental form, right? If you were to just like somehow magically remove some protons, then it would become nitrogen or carbon. Yes. It's no longer itself, basically, is what it is. And not necessarily a simpler substance, a different one entirely. Like if you could magically remove a proton from oxygen and a neutron and an electron, and you end up with nitrogen. Now it's not a simpler substance, it's totally different, right? It's not something we can magically just do. Yeah.
What's the simplest and most complex substance?
Huh? Define your question.
What would be the simplest of them all?
The simplest, well, if you're talking about with the least amount of subatomic particles, then you're talking about hydrogen.
What about the most?
Well, these are heavier elements, and some of these are like, when you get down here to these heavy elements, it gets real weird because there are some here that have been produced momentarily that aren't on here because they don't really like exist in nature. But I think we talked about the particle collider in France, CERN, right? So they'll slam particles into each other and they'll create a heavier element, but it can't survive. It's very unstable. All right, so what's an atom? All right, Yusuf.
The smallest particle of an element.
Yes, the smallest particle, yes. But what we're talking about there is the smallest particle of an element that is still that element. Yes, you can take an atom of nitrogen and break it into smaller particles, but it's no longer nitrogen. Now they're subatomic particles, right? There's protons, neutrons, electrons, so that's not nitrogen. Yes.
Can you use that definition for like water then? So it's like, yes, you can break down water, but then it's no longer water.
What do you mean? Say it again.
Well, you said, well, you can break down oxygen, but then it's no longer oxygen.
Mhm.
I said something about water.
Right, but water is not an atom. It's a compound. Right? Okay. Compounds always contain 2 or more elements joined in a fixed proportion. So Liam, definition?
A substance made of two or more simpler substances and can be broken down into those.
There you go. Can be broken down into those substances. All right, so you'll find next year in chemistry, you'll learn that there are some atoms that never like to be alone, and oxygen's one of them. Very rarely will you find an oxygen all one is lonesome. He likes to be with another oxygen or with another element. So oxygen is usually going to exist as an O subscript 2, two oxygens hanging out together. So in that case, it's not a compound because it's not a different element. It's just oxygen with oxygen, right? All right, now, mixtures. The properties of a mixture can vary because the composition of a mixture is not fixed. So heterogeneous, some people will say, but heterogeneous, okay. Okay, Jordan, what's this one?
Mixture in which the parts are noticeably different from each other.
Yes, okay, great example is this salad. It is a salad. Anybody who looked at that would likely call that a salad. However, there are lots of different things in it that you can tell from one another. The tomato is not the onion. The onion is not the nasty black olive. Ooh, does anybody like black olives? Did I just insult? I insulted Emily's black olives. I love green olives and calamari. I don't dislike black. I just don't love them.
How about all olives?
Yeah, Jason, whenever we go out, Jason gives me all his olives off his salads and I love it because they're great. And then a homogeneous, what's this one? Okay, Caitlin.
A mixture in which the parts are so evenly distributed that it is difficult to distinguish one from another.
Yes, you're correct. Something made him angry. Yes. All right. So a solution is an example of a type of mixture, but we have other types of mixtures too. It's an example of a homogeneous mixture.
I have a fun fact about pictures and the coffee picture.
Yeah.
That's soap bubbles, not actual bubbles.
Yeah, they do that. Have you ever watched any of the, what they call the food stylists is what
Yeah.
they call themselves, which I think is hilarious, food stylists.
Yeah,
But yeah.
Soap bubbles, not air bubbles.
Mhm. They'll put soap bubbles in there and stuff to make it look more appetizing. The ice cream is like Crisco and
It's-
stuff like that. And
I saw someone basically made Play-Doh for cookie dough ice cream.
yeah,
But it looks,
it looks delicious, doesn't it?
well, it also looks fake.
Because it doesn't go in the tank.
Yeah, they do all kinds of weird stuff I've seen. There's a lady on Instagram I follow who's always styling food. Yeah.
McDonald's burger,
Mhm.
they put card grease oil.
Drew. Sorry, Drew, turn off that timer on the oven, please. Thank you. That's my glassware.
They make
Done.
it look better in the commercials than it does in real life.
Yeah, they do. Yeah, they usually don't cook it all the way through.
They
Uh-huh.
usually don't even use real food.
James just had a great idea. What if the motor oil companies actually use syrup?
That could be not a lot of fun for the car owners, but interesting thought. It might smell real good when you're driving down there. Make you want breakfast. Yep.
Not feel good, but it might smell.
So we have different types of solutions here. So we have, I'm sorry, different types of mixtures. We have suspension solutions and colloids. So based on size of its largest particles, a mixture can be classified as a solution, a suspension, or solid. So a solution is, PJ.
A homogeneous mixture of dissolved substances.
Right, so coffee is a great example. It's mixed and today all of your liquids that you were dealing with were solutions, right? You can't tell one, I mean, we had what, magnesium chloride, right? That's MgCl. There's no, you can't see that in there, although magnesium chloride is a salt, so it dissolves very nicely in there, but you can't see it. How about a suspension? James. Soup, I was looking for a definition, but all right, I like soup. What's your favorite kind of soup?
Soup.
Tomato. Wait, no.
Chicken? There you go. Yeah,
Tomato soup, grilled cheese.
potato soup. So good example of a suspension is like an Italian dressing that you have to shake before you use it. Another good, if you ever want to design a suspension that you can play with again and again, you can get like various grits of sand and water and put it in a mason jar and shake it, and you'll see the heavier grit fall and it'll settle into layers. You can actually see it settle out into layers.
Oil, water, and glitter.
Oil, water, and glitter. And we've talked about in earth science, especially, and a little bit at the beginning of this year, but we talked about like stream erosion and so water and air erosion. One of the biggest things was suspension of solid particles within that fluid. So sand or gritty stuff within the water or within the air that's doing a lot of that eroding of surfaces as it hits, like all of those funky, hey puppy, all those funky sand sculptures that are left behind when you have wind erosion in the desert. All right, what's a colloid, Yusuf?
I can't raise my hand, but I'm raising my hand.
Sure containing. I got all different size particles.
Yes, and they're surrounded by smaller particles. So easy to remember is mayonnaise. Now, has anybody, I'm gonna tell you a story. Anybody ever seen what happens to mayonnaise when it gets hot?
Mm-hmm.
Okay, what's it do? It separates out, right? Because doing that takes away, colloids are usually stuff that is very, very thoroughly mixed. Like I have a mayonnaise recipe that came from my great aunt. She made the best homemade mayonnaise on the planet, but it's like an ordeal to make it because you have to constantly be whipping. Now we have stand mixers, but this woman stood there and did it in the kitchen with the, the mixer forever and her whisk in her hand. But so here's a story about a colloid, mayonnaise, easy to remember. You'll remember this forever. Hopefully, because it's so ridiculous. So when I was a kid, we didn't travel much because my dad owned a business and y'all met him. The man still thinks he goes to work every week, even though he doesn't go to work. Yeah, you miss, but he loves to go to work, even though he's not really working anymore. He's very dedicated to his job. So we didn't take very many trips, but we took a trip when I was about 10, I guess, to Big Meadows Lodge in the Shenandoah Valley. What a drive, look at the mountains. Spent like one night in a cabin before we had to go back to Virginia Beach because God forbid he not be there because of the business. Well, we went out for a big dinner and we were in this restaurant overlooking the beautiful mountains up high. It was gorgeous. We all had like steaks and baked potatoes and there was a side of sliced tomatoes. And my dad asked for mayonnaise because he likes mayonnaise with his sliced tomatoes. I do too. That's very good. So they brought in 2 little cups. You know, these little cups, they bring your condiments in, right? One of them had sour cream in it and one of them had mayonnaise in it.
Oh.
And it was dimly lit. And he tipped that whole tub of the mayonnaise into his baked potato.
Oh, no.
And a minute later, he looked down at it and it was starting to separate. It was no longer a colloid. Now it's breaking up. You got oils and fats and egg yolk and stuff like that in it. And it's all separating out. Well, instead of laughing at himself, for some reason, he became instantly embarrassed. So he put his hands around his plate like this, kind of trying not to let my mother see it. Well, she did see it. And she laughed at him so hard that the whole restaurant stopped working, stopped eating, and everyone was staring at our table. And my mother was in tears, like the kind of laughter that makes you physically hurt, like your sides hurt, your face hurt. And he's just like, stop. And it was something stupid, mayonnaise on a potato, but it was one of those things that will stick with me to the grave because my mom was just done. I mean, and my poor dad just sat there and everybody in the restaurant, the whole restaurant, what are they laughing at? So mayonnaise is a great example of a colloid. That is, it's put together with a good physical process. And if you start to take that physical process apart, because it's not a chemical change, it's a physical change. If it heats up, it comes apart. All right, so let's talk about some physical properties. We got a lot of definitions here. So examples are things like viscosity, conductivity, malleability, hardness, melting point, boiling point, and density. So a physical characteristic is defined as, Bailey?
Observable characteristic of a substance that can be analyzed without changing the composition. of the
Right, an observable characteristic of a substance that can be analyzed without changing the composition of the substance. So look at all these things here. These are all things you can observe without doing anything that's causing a chemical reaction, right? So viscosity is defined as, Ridley? Yeah, it's basically it's its resistance to flowing, but you can think of it like how thick a liquid is or how gooey something is, but how resistant is it to flowing? For example, water has a low viscosity, motor oil is going to have a thicker viscosity. All right, Caitlin, conductivity?
material's ability to allow heat to flow.
Yes, heat to flow. Also, there's conductivity with electricity, and these are linked, and they're linked for a good reason. When we get to chemistry and we talk about the structure of these particular metals when they're together, the way the atoms of each metal are going to align, a lot of these are metals, you'll see that it makes sense that electrons are able, the passage of electrons and charge, it makes more sense when you see how they're structured together. And when we look at our conductive things, we're looking predominantly at metals. So you can see here, you got transition metals, post-transition metals, metalloids, and then non-metals are your kind of weird ones in here. But like, where's copper? Somebody see copper? Anybody see it?
Yeah. Yes.
Yep, what's its symbol?
29 Cu.
29, Cu. Copper is Cu. Anybody notice on the copper sulfate over there, I wrote the formula and it said CuSO4. That's Cu is copper, it's cupric, basically, which you're going back to a Latin root in that case. Latin and Greek roots, always with the Latin and Greek roots. So this is a highly conductive metal, right? If you touch copper and it's hot, right? And if you try to send electricity through copper, it works really well.
But it's expensive.
Yeah, it's very expensive. It's so conductive that it's so expensive that people are now, Jason kicked the ball for him. That people are now like, remember we talked about people stealing copper wire out of houses under construction or abandoned houses? Yeah, it's crazy. All right, malleability is what? Emily, what's malleability? Yes, okay. So if something isn't malleable, do we know what the opposite is? What's the antonym for that? Scientifically, not flexible. Do we know? Do you know? Brittle's the one we're looking for. Yes. Okay. So some things are going to be more malleable than others. Obviously, one of our most malleable metals is gold, right? You can bite gold with your teeth and make marks in it. Yeah.
Yummy.
Yeah. So it's basically how can you hammer it? How can you form it and bend it without it shattering or cracking? And so let's think, if you're building a skyscraper, do you want malleable metal or brittle metal? Why do we want malleable metal?
Because of the wind.
Because of wind. What happens if it's brittle?
The wind will be so
Mhm.
hard, it'll just like break.
Yeah. Okay. So you know the stinky trees, the Bradford pears?
Yeah.
Okay. They're exceptionally brittle for fruit trees.
Jenkins.
And they will do you the favor of losing an entire limb when the wind gets high. Whereas if you look at pine trees, right, they're up high and they bend well. Yeah, that's true. Yeah, they only have a little tap root. All right, so what's hardness, Caitlin?
How hard it is.
Yeah, so it's, yeah.
There isn't a definition here.
Okay, so here's your definition for hardness. So it's your resistance to localized plastic deformation. We don't mean plastic, the substance. We mean plastic as in its ability to sort of bend or move. Kind of malleability is sort of similar, okay? So localized plastic deformation, that's like if I put a pinpoint of pressure in one spot and I press, how hard is this material? Is it going to chip, break, bend? Like some things are going to chip and flake like chalk. Chalk is not hard at all, right? You can actually run your hands over chalk and break pieces off of it, but you can't do that with iron.
Or diamond.
Or a diamond. Diamonds are very hard. So deformation, when we talk about, is a change in shape, and it can also mean you can just break too. All right, you want to give us melting point, Yusuf?
Temperature which substance changes from solid.
Yes, temperature at which a substance is going to change from a solid to a liquid, and boiling point is going to be somebody over here. Give me one of you two. Drew?
Temperature of material has to be at before it's boiled.
Right, but that, what is boiling? Changing from what to what? Liquid to a, not solid. Yeah, a vapor or a gas, right? Okay. So the temperature at which a substance is going to change from a liquid to a gas. Now, this is going, you're going to find this is going to be largely affected by pressure too, right? We're going to see a lot about that. We talk about Boyle's law, so talking about pressures, stuff like that. All right. And then, how about density? Liam,
I'll do an object.
what's that mean?
There's not a.
Can you
that
tell
was
me
the
in your words?
definition For hardness or density.
That's okay. In your words, what's dense? What's the, oh, who remembers the formula? Do you remember? Ooh, James and Colin want to steal it. Colin? Yes, you do. What's the definition?
Like how tightly packed the atoms.
How tightly packed? Yeah, do you know?
Mass over volume.
There you go. Liam was smart and did, what'd you just do?
I just looked at the triangle.
You looked at the triangle on the back of the binder. There you go. Yes, God bless your precious little formula triangles. Yes. So it's mass divided by volume. So remember we had like, if you compare a cork to a rock, a cork's going to have a lot less mass that's actual cork in the volume of the cork because there's a lot of air in there, right? Do any rocks float?
Yes.
Which rocks float? Yeah, lava rock, pumice. Yep.
Pumice, yeah.
Yeah, why?
Because there's a lot of holes in it.
There's a lot of holes. What's in the holes though?
Air.
Air, gas. Yeah, there you go. And that's not as dense as the rock. Yes.
Say density is how much stuff is in the thing.
Yes, how much stuff is in a given volume, right? Because mass is stuff, how much stuff there is, right? So how much stuff there is in a contained space would also be another way to do it. Okay, so using physical properties. Physical properties are used to identify a material, to choose a material for a specific purpose, or to separate substances in a mixture. So using properties to separate mixtures, we can do filtration and distillation are two common separation methods. So what is the method where we separate materials based on their particle sizes, Emily? That is filtration. And what is it when we separate them based on their boiling points? Okay, Jordan.
Distillation.
Distillation. All right. Somebody give me an example of what, where do we use distillation in everyday life? You know,
Beer and stuff, like.
beer's not distilled, it's fermented, but you're on the right track. You're on the right track.
Some sort of.
Some sort of alcohol in general. What? James? Water's distilled. Yeah, water can be distilled. All right. So Liam was onto something. Yes. So when you hear people talk about spirits or distilled spirits, that's the alcohol that's distilled. You ever seen like, what's that show? Moonshiners? You ever seen that? Where I swear those people are actors. There's nobody that hillbilly on the planet, but I should probably take that back because they probably are people that they're really, yeah. They had that, what was the guy's name? He had two names. He's like, I don't know, like Bob Sam or something. And he always wore overalls. He had a still going. Well, the way the still works is you put your mixture in, whatever you've got, usually some kind of a grain or a fruit and water, something with a sugar source, right? And you're boiling it and you have the alcohol mixed in, but it's mixed in with all the whatever fruit and mash if it's grain, right? You boil it, that alcohol is going to boil at a temperature that is going to allow it to go up high and catch into this thing called a worm. It goes through this like condenser, right? And then it comes out the other side. And that's where you get distilled spirits. But yes, water can be distilled. This is basically means the water's been boiled and then the boiled vapor, the vapor is collected, condensed, and then that's what you're drinking. So that means there's no other particulate in it, right? Like if you're camping, sometimes they have those little kits that you can use where you can like boil water and it catches it, brings it back down, cleans it out for you. There's no something you don't want, basically, right? All right, so a physical change is what? Who can give me a physical change? Okay, PJ, you go. Yep, she's looking.
Some
You're right. Some properties.
properties of material changes, but substances in material, the material remains the same.
Right, okay. Oh, I wanted to say one more thing about filtration. We will be doing filtration next year. We do use vacuum filtration. So we have a vacuum pump and you hook it up to a little guy like this and you put like a little funnel on top and some paper that catches all the particulate. It's pretty fun.
I don't do that one.
Yeah, you did. We did a couple of them.
I thought it was one of those like, because it was like right after COVID though.
Yeah, we had a couple that had to go on.
Oh, was it like the 2 cigarette?
Yeah, that one was online entirely because the whole world shut down again. Yeah. So this right here, you have paper. You fold the paper, it becomes an airplane. Good example of a physical change. Yes, it's an airplane now, but it's still paper. You didn't do anything to change it except fold it up. Changed its form, its purpose maybe, but it's still the same substance. All right, so let's talk about properties, observing chemical properties. Chemical properties can only be observed if the substances in a sample of matter are changing into different substances. So what is a chemical property? What's the definition there? All right, Liam.
Material's ability to produce a change in the composition of matter.
Yes, the material's ability to produce a change in the composition of matter. Remember, matter is stuff. So what is the stuff made of? So its ability to produce a change in what something is made of. So flammability is a property. Emily, what's flammability?
Material's ability to burn in the presence of oxygen.
There you go. Material's ability to burn in the presence of oxygen. And reactivity, Yusuf.
How readily a substance combines chemically with.
Yes, how readily it combines with other substances. Okay, so the stuff you had today in lab, we were putting chemicals together that have some level of reactivity with each other, but that doesn't necessarily mean it has reactivity with everything else. But some things are more reactive than others. Some chemicals are very reactive with like even the tiniest bit of environmental impact. So there are certain metals, for example, that are very soft and they're usually stored in some sort of liquid because when they come in contact with oxygen, or some are stored in oil because when they come in contact with water, they will immediately react. There are some great videos of people throwing like sodium out into ponds just for straight up sodium and like, whoa, I mean, it'll for real explode. Yeah.
I think I found a brownie point. It says Guy Lussac.
Guy
Law,
Lussac?
but here it says Gay Lussac Law.
It's Guy, but it's not Guy because he's French, it's Guy. So, or gay. No, it's gay.
You.
Yeah, I think I've seen it both ways, but I'll double check it. Pretty sure it's Guy. So, chemical properties. Here's some other examples. We did flammability, we did reactivity, but we also have toxicity. That's a good one. How poisonous is this? Some things just touching it. Great example would be mercury. All right, mercury is cool because it's a metal that exists at room temperature in liquid form, right? And like when I was a kid, if you had a mercury thermometer and it broke, you'd be like, "Whoo!" You know, no, not the smartest thing to do, but we did it. Mercury in particular does anybody know the historical root of, think about Mercury in Alice in Wonderland. Does anybody know the link? Do you know? You know it. Yeah, and I could tell you knew it immediately. Yeah, the Mad Hatter. So hatters, people that made hats, used mercury as part of the process. And it caused them some brain damage. And yeah, a Mad Hatter was a thing. It's not just an Alice in Wonderland character. It was an actual thing. Yeah.
Must have with a liquid sits at room temperature.
Mhm.
Gallium's a good one.
Yeah.
It doesn't hurt you.
Yep.
Unless you're.
We
a
have
robot.
gallium. We have some gallium that you can touch and it's pretty cool.
It's only reactive to aluminum, right?
Not just aluminum.
I'm not sure. I don't remember
Yeah,
all of them
it-
off the
it
top of my
does.
head. Yeah, I think you're probably right. But yeah, I know it will. If you put it on aluminum, it grows. Yeah, it'll look like, yeah.
No, it'll crunch the aluminum, it'll look like powder.
Yeah, but it's-
It'll dissolve the.
That's right. Yeah. What's the limit? Something grows with gallium though. I don't remember what it is. I have to remember. But yeah, so toxicity. The other metal that we think about with toxicity that affects, do you know?
Uranium?
Uranium, yeah, well, radioactivity there with that one. But toxicity that we're still having to be aware of because of our own industrial goofiness, you know?
Radon.
Radon ends in basements, and now you get some radioactivity too. I'm thinking about lead. So it's not so much a thing too much anymore, but lead used to be put in paint as a standard. It helped brighten the colors. And yeah, it's in pipes too. Yeah, but it used to be a standard for paint. Okay, so back in the 80s or early 80s, they started making a push to have every house checked for lead. So when you buy a house, they'll check it for lead even now most of the time. So because lead paint, you'd slap it on your windowsill, and you've seen old houses, I'm sure, where the paint's chipping. Well, little kids would pop those paint chips in their mouth, and then that's really bad news. So yeah, because little kids will put anything in their mouth, or they'll chew on the windowsill while they're looking at, babies. It's really not good. Heat of combustion is how hot you have to get it before it just bursts into flame. Oxidation states, we'll talk about oxidation reduction reactions next year. Stability, flammability, coordination number. This has to do with what it reacts with. And reactivity, possible bonds, again, what it reacts with. And then enthalpy of formation. We'll talk about enthalpy next year. We talked about it a little bit this year, but it's basically like how organized is something? And that things actually want to be in the simplest organization. So recognizing chemical changes, 3 common types of evidence, but there are more than 3. Okay, your book, I think, listed 3, but there are more than 3. And these are our main 3. We have light release, temperature change, production of a gas, formation of a precipitate, and color change. And there was another, see, there's 5 here, but there were, we listed 6 before. We'll go over them all next year. It's all 6. Yeah. I think we came up with 6 in class today, just kind of offhand, but yeah. So chemical reaction, Liam? He's like, I had it, but I don't have it, but I have it. Where'd it go? Caitlin, you want to steal it?
Reaction of substances from which beneath.
Oh, that's what.
Which form one or more new substances, right? Odor, yeah, it's missing odor for sure.
Taste.
You don't taste the chemical.
Why not? Exactly, why not?
Mhm.
Unless you wanna die.
Okay.
So yes, you're talking about when you have substances that react and they produce one or more new substances. So the most obvious one today in class was the one that I put up the formula for, which you had what? Magnesium chloride and so would you have sodium carbonate, and then you ended up with magnesium carbonate and sodium chloride. And that was a reaction that caused a precipitate to form, right? You saw that cloudiness in the test tube. Yeah, that's what you had. So when matter undergoes a chemical change, the composition of the matter changes. When it undergoes a physical change, the composition remains the same. And that's the thing to remember. So your precipitate, which we just talked about, is what is a solid that forms in your liquid mixture. Now, precipitate, we talked in science and a little bit at the beginning of this year, we talked briefly about minerals and stuff, that precipitate can also be considered something that if you evaporate all the water out of a solution, what is left behind? For example, salt can be left behind, stuff like that. You can see that, like you get rocks and stuff that are made of that, right? All right, now, solids, liquids, and gases. All right. Materials can be classified as solids, liquids, and gases based on whether their shapes and volumes are fixed or variable. So a solid is defined as, Ridley?
Fixed object that doesn't change.
Yeah, fixed shape and fixed volume. So its volume and its shape don't change, right? Definite shape, definite volume. All right, Drew, liquid?
Fixed volume, but no fixed shape.
Fixed volume, but no fixed shape. If you pour your liquid from one container to the next, it's going to take the shape of its container, but its volume will remain the same. And then Jordan, how about a gas?
It has no definite shape and no definite volume.
Definite shape, no definite volume. It will fill whatever container it's in, shape and volume. And then Colin, plasma. Do you know this one? Ah, okay, so plasma. So plasma is really possible at all, yeah, very high temperatures. This is not something that exists in your everyday, I see this all the time around me, whereas you can see solids, liquids, and gases around you all the time. Light, like lightning is plasma. Light itself, we know, is an electromagnetic wave. It's also a particle, but what's producing the light in those cases, like for lightning, is plasma.
Yeah, that's it, lightning is.
Lightning is in it, yeah. So if you're looking for plasma, that's a good place to see it.
The fifth one is like something like B.E. Boyd, Einstein, something.
Yeah.
That's what low temperatures.
Yeah, like real theoretical, like Kelvin.
That is possible.
Yeah, we'd have to get us there.
Bulbs use some form of plasma.
Most of the time when you get a heating element like that, there's some degree of that going on. I mean, a filament, that's the word I mean, somewhere in there. Yeah, there's some degree of it. But the what? Yeah, the sun, there's obviously plasma there. And then also if you see electrical arcing, like psh, you can see the plasma there when you got sparks flying and stuff.
Also, the matter that surrounds black holes is also plasma.
Okay, matter around black holes is plasma. There you go. So kinetic theory of matter states that all particles of matter are in constant motion.
You're moving around.
So kinetic energy is simply defined as, Jordan,
Energy of motion.
energy motion. We know this. We've done kinetic stuff all year. All right, so here's a couple things for you. Gases. There are forces of attraction among particles in all matter. Kinetic theory of gases says the constant motion of the particles in a gas allows a gas to fill a container of any size or shape. Now, liquid too can take the shape of its container because the particles can float in new locations, but the volume is constant because the forces of attraction keep the particles close together. Now, real quick, we said that they can't change volume, gas and liquid. That's at a steady temperature and a steady constant temperature and constant pressure. If you put a gas in a situation where you're making it very, very hot, it is going to change volume to some degree. It will expand. If you're going to cool it, it will condense, right? And same thing for liquids, with the exception of one liquid. Bailey? Water. What's interesting about water?
It has,
Kill you, but also.
Yes, this is true.
and unlike a lot of things, when you condense it,
Mhm.
it's the opposite.
Right.
When you condense it, it actually will expand
Mm-hmm.
because of ice. And
Right.
when you boil it, it actually shrinks, not as much as.
Yeah, it's more along the lines of what I was thinking, more along the lines of, yes, the first part. So water, when you cool it, it will condense to a point. And then when it freezes, the water molecules are going to structure themselves in a crystalline pattern. So it is going to necessarily increase in volume, which is why anything you put in the freezer should not be filled to the brim when you close the lid on it. That's not going to be good for you because it's going to break the container when the water expands.
Pour Coke.
Yeah, a Coke.
Oh, yeah.
Coke in the freezer.
Oh,
Everybody's
good
done
idea.
it. Everybody wishes they hadn't done it. Coke in the freezer.
No, Melissa's really careful.
careful about that.
Y'all are smarter than most, cause it happens and it's not a ton of fun, but yeah, Coke in the freezer.
And I'm not allowed to try it.
Yeah, I wouldn't recommend, I would say, like, last night may have been a good night, like, if you'd had a Coke and you'd kept it in the freezer in your house for like 30 minutes to get it good and cold, and then you put it out last night when it was 29 degrees inside a box.
Oh, yeah.
Like, and then went and looked at it in the morning, you could see the damage it's done, but yeah, it will kaboom everywhere, and it will kaboom more than just regular liquid, because it obviously has gas that is in solution, which is going to rapidly expand when that container is no longer closed. So just like when you open it, it goes and you have a gas escape, you're gonna get gas escaping and super cooled water in there, and it's gonna make, like, it'll look like a cave. There'll be stalactites and it's fun. Yeah. Okay, and then, what now?
There's also a thing, I think also if you like leave it in the car or something, it also bursts.
If you leave it in there, it's really cold or really hot. So solids have a definite volume and a definite shape because the solid particles vibrate around fixed locations. Okay, you ready? In a minute here, we're gonna pop up our favorite chemistry resource. Dr. Dave. We're gonna, Professor Dave is the coolest human. We're gonna bring him up in a minute, okay? And he's gonna be talking about these kinetic theories here where gases are involved. All right, so what do you call force over area? Everybody should know this one. Emily? Pressure is force over area, right? That's a very definition of it. So collisions between particles of gas and the walls of a container cause pressure in a closed container of gas. Factors that affect the pressure of an enclosed gas are its temperature, its volume, and the number of particles. So temperature. Raising the temperature of a gas will increase its pressure if the volume of the gas and the number of the particles are constant. Absolute zero or 0 Kelvin is when all particles cease to move, which is, again, very theoretical, right? Volume, you can reduce the volume of a gas and it's going to increase its pressure if the temperature of the gas and the number of the particles are constant. We'll actually do this next year. You'll have like a 2-liter bottle and you'll seal it up nice and tight, and then you'll crush it against the side of the counter with all your body weight, and you will watch the temperature change.
Is that what I was?
It will increase because you have increased the pressure.
What you get to do was a little thing where you twist the bottle, empty water
Oh,
bottle.
Oh, and make
I
the
love
cloud?
doing that. That's so fun.
Yeah, and make the cloud. That's also related to pressure. You will make the
That's so
cloud.
fun.
That is fun.
It always scares everyone in the car.
Tried that,
Probably Michael or Cole.
probably.
One of them. Yeah.
Probably.
So the number of particles, increasing the number of particles will increase the pressure of the gas if the constant temperature and constant volume. So you see, we got examples of each, and these are our gas laws. There's actually 4, but when you get them all combined, you get ideal gas laws and combined gas laws. And here's our favorite, Professor Dave. So for those of you who haven't done chem, and he shows up for a couple other subjects, but he shows up a lot in chem.
You're a bit first.
Yeah, we've had a little bit of him for earth science. I think we may have had him once or twice this year, maybe, but this dude is super duper freaking cool. And his videos are great because they're relatively short. They're clear, they're concise, but you can't look away. Like, he gives you information like this. You can't zone out on Professor Dave. You'd fail his class. So this is kinetic molecular theory and ideal gas laws.
Hey, Professor Dave, let's talk about ideal gases.
We love
Let's
that.
recall our definition of a gas as the phase of matter where atoms of a substance are in motion and fill their container. If we make a couple simplifying assumptions about gases, we can make some easy predictions. Those are that 1, particles of a gas are dimensionless points in random motion, and the identity of the gas is irrelevant. Could be anything. And 2, that the particles don't interact apart from elastic collisions, bouncing off one another like balls on a pool table. These things aren't completely true, but they make the math easy and surprisingly accurate. So these kinds of samples are called ideal gases. When examining an ideal gas, we want to be able to discuss 4 variables. 1, pressure. This is the force the gas is exerting on its container, or rather, how much the particles are hitting the sides. 2, temperature. This is the amount of heat energy available to be transferred into kinetic energy of motion. The higher the temperature, the faster the particles move. 3, volume. How big is the container? And 4, moles. How many particles are there in the container? So, how many particles? How big is the container? How are the particles moving and how often do they hit the sides? As it turns out, these variables depend on one another in interesting ways that have been formulated into laws. Let's look at the piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed, if we compress the volume, the pressure must go up. The particles will be hitting the sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional. If one goes down, the other goes up. This is expressed in Boyle's law. P1 V1 equals P2 V2. If we double one variable, we have to cut the other one in half in order to keep this equation valid. Volume and temperature are also related. If we have gas in a balloon and we heat it up, the particles will move more quickly. In order to keep pressure constant or hit the sides with the same frequency, the volume will have to expand. This means that the volume and temperature are directly proportional. If one doubles, the other must double. This is expressed in Charles' law. When we do calculations with temperature, we must always use an absolute temperature scale called the Kelvin scale. 1 degree Kelvin is the same magnitude as 1 degree Celsius, but 0 Kelvin is absolute zero, the lowest temperature possible, a complete absence of heat energy. This helps us avoid weird mathematical issues that would arise if we were doing a calculation involving a negative or zero temperature. To get Kelvin from Celsius, just add 273. To go the other way, subtract. The combined gas law is like a combination of Boyle's and Charles'. Avogadro's law says that equal volumes of gases at the same temperature and pressure contain the same number of molecules. Specifically, that 1 mole of ideal gas occupies 22.4 liters at standard temperature and pressure, regardless of the identity of the gas. Lastly, all the variables correlate in one equation called the ideal gas law. This also contains the gas constant R, which makes these calculations intelligible in our man-made units. There are a number of values for R depending on the units, but we will predominantly use this one. This equation is useful when we aren't looking at a change, but just to know the values of all 4 variables at once. Like in this case, we could know the pressure, temperature, and volume of a gas and quickly calculate how many moles of particles must be in the sample. So if you were looking at a sample of gas and you have 3 of the 4 variables, you can solve for the 4th using the ideal gas law. If you are given some initial conditions as well as some final conditions, you can use one of the other laws to find the other information. Just plug in what you know and solve for what you don't. Let's check comprehension.
I love let's check comprehension. And he always has this little like bossa nova style 60s elevator music. And then he shows you the math. We love Professor Dave. Professor Dave's the best.
Professor David.
Okay, so it is Gay is Lasac's law, and it's autocorrected wrong here. Like I was saying, it's a French name, so it autocorrects it as Guy because Guy is a first name in French. Guy.
Not a brownie point?
Yeah, you got one. So yeah. All right. So and I copied and pasted it, and I didn't even catch it myself. So all right. So Boyle's law. Let's see, which one of these was first? Boyle's law. Okay, who can tell me what Boyle's law is again? All right, Bailey.
Pressure of a given mass of an ideal gas is inversely proportional to its volume at a constant temperature.
All right, so the pressure is inversely proportional to its volume at a constant temperature. All right, how about Charles' law? Who wants to go there? Yusuf?
The volume of an ideal gas at a constant pressure is directly proportional to the absolute temperature.
Mm-hmm, yep, okay, so here we're doing temperature and volume with Boyle's, and we're doing pressure and temperature with Charles. I should say Gay-Lussac. Gay-Lussac's is, who wants to go there, Liam?
The pressure of a given mass of gas varies directly.
Okay. Yes, pressure temperature is this dude. This guy was, well, this guy's pressure temperature as well, so it's kind of harder to break down. But this is saying the pressure of a given mass of gas varies directly with the absolute temperature. And so combined, what does it mean? When we put them all together, we have a combined gas law. Caitlin?
The combined gas law combines the 3 gas laws.
Yep, it combines the 3 gas laws. So Boyle's law, Charles' law, and Gay-Lussac again. So it states that the ratio of the product of pressure and volume and the absolute temperature of a gas is equal to a constant. And then this is the constant, basically. It's this whole PV equals nRT, and here we have PV over T equals K. There'll be a lot of that next year. Not as much this year. So characteristics of phase changes. So these are physical changes, right? Phase. All right, so melting, freezing, vaporization, condensation, sublimation, and deposition are 6 common phase changes. A phase change is reversible physical change when a substance changes from one state of matter to another. The temperature of a substance does not change during a phase change. It has to change prior to the phase change, but it doesn't change during the actual change. There is a point at which it's constant. This may be instantaneous, but
If you're boiling a pot of water and you get it 200 degrees Fahrenheit, it'll start to vaporize.
yep,
The temperature won't get above 212 until all the water's gone.
exactly. Yep. Same thing with freezing. Like it can continue to get colder outside, but that ice is going to be right at your 32 Fahrenheit, right? Now you can get that colder, but you actually, what then you get is some sublimation going on that you don't see. But, all right. So energy is either absorbed or released. So what do we call a system that absorbs energy? All right, Yusuf?
Endothermic.
Endothermic. So now there's something called the molar heat of fusion. So this is heat absorbed by a unit mass of a given solid at its melting point that completely converts the solid to liquid at the same temperature equal to the heat of solidification. Blah 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 blah. Don't worry about it too much. Next year becomes more of a thing. And then what is a system that releases energy, Emily? Exothermic. Okay. Now, absorbs energy, releases energy. This has to do with whether or not something feels hot or feels cold too. Okay. When you're doing chemistry, when if you have a container in your hand and you feel warmth, your temperature change, or you might feel cold, like those ice packs, the little ones that you pop and shake, or the heat packs that you pop and shake or mix together, and suddenly they get very warm or very cold. If you are absorbing energy, it's going to get cold. If you're releasing energy, it's going to feel hot. So melting and freezing, the arrangement of molecules in water becomes less orderly as water melts and more orderly as water freezes. So you have vaporization and condensation. Evaporation takes place at the surface of a liquid and occurs at temperatures below the melting point. This is why, boiling point, sorry. This is why puddles outside evaporate, right? It doesn't have to boil for that liquid to change into a gas. It's because it's just at the surface. So what's a phase change from a liquid to a gas?
Vaporization.
Yes, okay. Phase change from a liquid to a gas is vaporization. Now there are types of vaporization. So we talked about the heat of vaporization. That's when it's going to vaporize. So our two main types of vaporization, we have a phase change from a liquid to a gas at temperatures below the boiling point, which is what? We just said it about puddles. Yep, go ahead. Evaporation. And then a phase change from a gas or vapor to a liquid, Emily? Condensation, that's it. The opposite. So I said we have two main types of vaporization that we talk about. If evaporation occurs at the below the boiling point, then what's the other one I'm talking about? What's the other type of vaporization? Not evaporation, but not sublimation, but it could be. I'm talking about, what do you think?
Deposition.
No, I'm just talking about just what? Just boiling. I mean, if you think about it, you've got evaporation where you've got a phase change, but it's below temperature. The other way you can get something to vaporize is at its boiling point. Okie dokie. So, coins. Okay. So what is a phase change from a solid to gas or vapor without first changing to a liquid, James? There you go, sublimation. So now they have these sublimation printers, right? So basically they have a solid And they're putting the color on t-shirts and stuff exactly the way you imagine they would. It doesn't really get, like, it's not really a liquid ink. It's like a solid that gets sublimated directly to a gas, and then it's a solid again when it hits the material. Uh-huh.
Video eating plastic ice.
Yes, the dumb plastic ice. You remember, right? So we've talked about this before, especially when we do meteorology and earth science, that every year there's some idiot. You can count on this, guys, and social media has made this idiot, whoever this idiot is, it's multiple idiots, but it's the same idiot, more prevalent. But this is the, whoop, somebody's phone's ringing. Okay. Does it say like mom or something on the screen, Asher?
That's.
Oh, that's Emma's phone. So,
I can. We're singing Jack on Thursday. Yeah.
I'll tell her it's here too. Give me 2 seconds, because that's Emma's mom's probably gonna call 50 times, because now they're looking for the phone. Hold on,
Just saying FaceTime, so the link, that's right.
it's here. That's all I said. It's here. All right, so, yes, so that's our sublimation. And what we're saying is there's always an idiot with a snowball every year. Every year, there's somebody when it snows who packs the snow into, she did not see my text, into a little snowball. And then that person, yeah, she just saw it. And then that person will take that little snowball and they'll light a lighter to it, and it doesn't drip and it doesn't turn to water. Instead, it turns black, and they go, it's not real snow, it's the government putting plastic snow down. And no, it's not. It's sublimating because it's so hot right there next to it. It's just sublimating. And it's just soot from the butane and the lighter. This isn't rocket scientist, but every year you watch, it's a guarantee. We didn't get any snow this year, so we didn't get to see that idiot, but that idiot will arrive every year. Scientific illiteracy.
Plastic snow.
Yes, nobody's
and
doing the
it's still
government.
fun.
Yeah, there you go. I agree. So what's the phase change from a gas or vapor to a liquid? Jordan.
Deposition.
Deposition, right. So this is how you get dew, right? If you see dew out on the grass. Oh, we're fine. We have pottery this afternoon. Sure. Get back to you when I'm done teaching. Okay, sorry. She's like, we come by, can we get it this afternoon? Because she straight up left her phone here. Oh, okay, it happens. Next up. Now we're gonna play our game. Okay, we probably have enough time. So a couple things first. I'm gonna give you the directions for this game first. We're gonna divide into 2 teams. Now, something to remember to keep in context is we do have to kind of keep the volume down a bit, you know? I know games are exciting, but we have to keep the volume down a bit because there is a man who works here. Yes, question.
Is squealing pig.
No, there's no squealing pigs in this game. Although I love the squealing pigs, they're not in this game. So here's the way this game's gonna work. You're gonna divide into 2 teams and listen, make sure you're listening. I got one bed, here's the other one. Your 2 teams. Not my name. Where did it go? Okay, each team. Oh, okay, thank you. So we have 2 teams. Each team is going to get a little bag, okay? And I'm gonna give you about 3 or 4 minutes to organize first. So I'm gonna take Bailey, PJ, Caitlin, Liam, Jordan, and Yusuf as 1 team. We're actually gonna go in the dining room and we're gonna line up on opposite sides of the table because you kind of need to see a surface, but don't go yet. Let me explain.
Is Emily also part of yours?
Well, that's 6 and 6, so it works out. So here's how it works, okay? Each of these bags has in it both terms and definitions, all right? So you're gonna divide into 2 teams. Team 1 is gonna have vocabulary words and definitions. Team 2 is also going to have vocabulary words and definitions, but they match the other teams. So if the vocabulary word is on this team, the definition's on this team. If the vocabulary word's on this team, the definition's on this team. They are like puzzle pieces, so you know if it's right because I've trimmed them so that they actually fit together, the definition and the term. So what you do is you're gonna take about 4 or 5 minutes and organize your materials. So I would do this by kind of, how are these terms related? Are these definitions of types of physical changes, definitions of matter, atoms, what is related, okay? And then team 1's gonna read aloud 1 vocabulary word or 1 definition, okay? And then team two, and you don't have, you can read it aloud and then put it down, but you can hold a finger over the little shape where it's cut so that it makes sense if I show you what I mean. So when you put it down, for example, this one, you can put it down on the table and hold your finger here because the other team is looking for that shape on their side, right? Okay, so the other team is gonna have 15 seconds to try and find the match. If you find the match, that team gets to keep the set. If they don't find the match, you just put the word back into, or term or definition back into circulation. You don't get to keep it yourself if you're the asking team. The only way you can get a match is if you answer correctly. And then you go back and forth doing this. The only thing you have to do, being careful, is if you get a match, okay, I'm gonna take your match and put it on your side of the table, but I'm gonna position the two parts of your match so that when we're done, I can separate them back correctly so that your definition goes back to the side it belongs on, and vice versa, okay? So let's come in here and let me take this. Okay, so I'm gonna give you about 45 minutes to organize. So one side over here, one side over here, divide down the middle this way. Turn on lights, you can actually see what you're doing. So you're gonna get a turn to do both. Let's see. You guys can ask first and you guys can answer. Those are the terms. Yep. And I will end this because there's nothing else to see.
Yes.